All right, guys, we're gonna go ahead and get started with the lecture today. Okay, cool. So today we're gonna be covering RNNs. So I don't know how many of you guys have prior experience with recurrent neural networks, but that's totally fine. We're gonna go start from the basics once again, and start from where we left off last time, and proceed with the first understanding the architecture, the philosophy behind recurrence, and then we're gonna finish up with LSTMs, a quick vanilla lesson on LSTMs. Okay. Okay, cool. So last time, or I guess a couple lectures ago, we know how the basics of neural networks work by now, right? Like we understand that given different features, predicting some numerical output or some classification output, we know that it basically follows the regular architecture of what a neural network is. Your input nodes feed into the next layer. Each node and layer communicates with every node in the layer afterwards. And then finally, your output layer is the amalgamation of the layers intermediate, right? And so basically, afterwards, we even talked about CNNs, which is how do we classify an image? How do we work with some type of visual input that we can then convert into a strip, convert into some type of encoding for the image, pass through convolution layers, max pooling layers, dense layers, and then output some type of function that we want to understand and make sense of an image, right? But one thing that we didn't really talk about explicitly is how we're going to handle this idea of sequential data, right? Many times we want to model data that has a temporal dependency. And so what do I mean by that? I mean, predicting the next day's stock price, predicting the next day's weather price. If there is a ball that's moving, across the screen, like where will it be in the next time step, right? And so this type of data is inherently different from the images that we looked at before, obviously, but from the main premise of a regular vanilla neural network that we've been learning up till now. And the main idea is this, right? Like, imagine we wanted to predict sequential data. Well, inherently, we need to have some idea of what the data looked like before we want to make a prediction. For example, we can't predict day 6 weather data or stock data with just having day 5s. It doesn't work that way because we want to be able to capture the relationship of how a certain value is changing over time, and then use that intuition to generate a prediction for the next time step. This makes sense to us, right? The idea that we want to be able to have like some type of temporal dependency that's captured by our model to predict a value output for the next time step. In other words, we need to have a memory of what happened before. We need to be able to say, I know what happened on day 1, day 2, day 3, day 4, and day 5, and because of that, I can now predict maybe stocks will go up on day 6, right? If I'm lucky. So I guess let's try to model sequential data with everything that we know right now. Okay, let's just try our best, given our original vanilla neural network that we've been learning until now. How do we model sequential data? And the most naive way to go about this is we'll take values for every single different time step that we currently have. Okay, we'll take values for each of the different days that we have, each of the different sequences that we have, and then we'll just make them all equal to the input layer. In other words, if we had day 1 stock price, day 2 stock price, day 3 stock price, we can just make them be the first node, second node, and so on and so forth, and we can just have the entire input layer correspond to the sequential data. Okay, does anyone so far think there's any problems with this? Yes.
Like when you add another day, it's not gonna have any like way of like it'll just be like completely random basically when you add like the next day and try to predict the day after.
Exactly. So he picks up a great point, right? And that's a really key point. We can't handle variable length input. You hit it on the nail. Like if we just train on the first 5 days, for example, how are we going to use that to predict the 6th day? What, we have to go in there and add another node at the end. We have to connect that once again, but we can't do that when we're training. We can't do that during backprop. What we have is what we get in the beginning to start off with. Okay, so fine, let's say that we find some way to, fix this somehow. Or in general, is there any other issue that someone else can point out with this architecture or with this idea? So basically, there's no explicit dimension of time. We are giving this model access to entirety of the prices from day 1 to day n all at once. In reality, it's the case that day 1's price affects day 2nd. Day 2nd affects day 3rd, day 3rd affects day 4th, and so on and so forth, right? So if we just input all the different day prices all at once, how can we expect the model to understand that the prices have been fluctuating throughout the first couple of days, and because of that, there is something that needs to happen with the last day there? There's no way that we can get the model to understand that temporal dependency, which is key for the certain problem that we have. Does this make sense? And so the idea here is key. We want to be able to have the prediction of a day or the prediction of the next time step depend on our understanding of the time step before. In other words, we want to make sure that our prediction of the time step in the future depends on our prediction of the time step in the past. For example, if we want to predict the temperature of day +1, then we want to be able to have that influence the model's decision for the next prediction. Day 5 is going to affect day 6, day 6 will affect day 7, and so on and so forth. We want to imbue our understanding with the neural network with this idea of recurrence, or this idea of, this idea of having recurrent information, depending on information from previous time steps. So I guess up till now, people understand, hopefully, that in order to model sequential data, we need to inherently change something with our neural network. We have to add in a recurrent connection that can teach the model to understand that the previous time steps actually matter for predicting the next time step it needs to predict. That the previous time steps from like 1, 2, 3, 4 matter when you're predicting day 10. So the question is, how are we going to do this? And for simplicity, before we had a layer that had a ton of different neurons, we don't need all of that. To explain what I want to explain, we can just condense this down for simplicity's sake in just a one neuron, all right? So imagine the trivial neural network. You have some input node, the intermediate, hidden layer, which is just one node, and then you have, the output layer, which is just the output node that we have. And each arrow here, to clarify, represents multiplying by a weight, adding a bias, and then passing through the activation function like we discussed, as usual. And there's one thing that we want to be able to do. We want the information from the layer of the network, once you make the prediction, to go back and influence prediction at the next time step. Which means when you have day 0, you want it to be able to, the prediction that you have at day 0, we want it to be able to go back, and then when you increment day t to day 1, you want that day 0, 1 to come back and to help us predict day 2. And in other words, what we really want is something like this, right? And I explicitly made the arrows, the weight and the bias here, just so we can explicitly what's going on. But we basically want some idea of what the prediction should be at time step t to go back in to the next iteration, in which at time step t + 1, it'll help it predict it. So I guess a question that you guys might have is, okay, I understand that the prediction for the weather on day 0 has to go back and influence prediction of the weather for day 1. But why are we taking it after the first activation function here? Why are we taking it, prematurely, you might think, before it passes through the last weight and biases? Like, shouldn't we just be taking it from predicted data, t + 1, and then, sending it back somehow to influence, how the model will learn? And before we kind of talk about what's happening in this diagram and how we're establishing a recurrence network, there's one key intuition that I want to pass on to you guys, and that is the role of the activations of the neural network. And so the main idea here is layer by layer, the input goes through from one layer to the other layer, passes through the activation function, and then transforms itself one layer at a time. It's kind of like going down a stream and passing through one dam at a time, with each dam being a different layer. At every step, you're changing a certain way, you're passing through a new activation function, and finally you make it to the last layer, and get transformed into the output that we need. This right here is the temperature. It's the stock price. It's the actual raw price. But we have to understand that this last layer's weight and bias, its whole job is not to, add much more intuition that's already been gained from the relationships, but just to transform it into the form that we need for our output. The last layer's job is just to transform its, I guess you could say, understanding as it passes through the model into the form that's needed for our output. So in reality, it's these activations that sort of carry forward the model's intuition and understanding from one layer onwards. So no matter what, we want to be able to take an activation and send it back to the next time step. But we want to take the penultimate activation, the one right before the last layer, because this represents the raw knowledge and raw intuition that the model has before it just adds some surface level, shift to transform it arbitrarily into the form that we need for a neural network. So I guess before we even talk about what happens in the diagram, does everyone understand like the specific role of like that penultimate activation layer and why we're kind of cutting it short there to send it back? Does that sort of make sense to everyone? Okay, so what's happening here? We're gonna take that activation, right? The output of the activation layer. We're gonna multiply it by some weight, we'll call it W2. And then we're gonna add that to the sum of adding the bias. So after the inputs multiplied by weight and added the first bias B1, we're gonna add that to this activation times W2. And that new sum is going to pass through an activation layer again and become the next time steps prediction. And we're gonna go through a concrete example, obviously. But maybe another question you guys might have is, why are we multiplying by that weight? Why can't we just, I guess, take it and then add it if we just want to remind it of what the activation was from the previous time step? And to this, I want to basically clarify that the assumption here is that that previous activation is the closest we're going to get to that raw understanding. But if there's ever like some area for improvement, this weight is something that we can backprop on later to adjust what the understanding is going to be to better reflect like the perfect, I guess, like combination that can get us a representation of what the understanding was at that previous time step. So by simply slapping a weight 2 on it, by slapping a weight and modifying it, we're able to now backprop on that representation, on that intuition, on that understanding, and refine it and tweak it to better match our accuracy of the model. So we're basically connecting it the same way you would for any other given layer. So let's go through just on day 0, right? Just what is this new recurrent relation that we added? Yeah, what was the question? Oh, sorry about that. So I guess what would happen on the first sort of pass through, right? So on day 0, let's just say that we input, let's just say day 0, that we don't have any data for it. We basically input some 0 value, right? 0 multiplies by, our 1.5, which is W1. It adds to bias 1, and then it pauses. And then notice how this is the first day, so there's no days like before it. So because of that, there is nothing that is recurrent in nature here. There is no previous time steps, like, hidden state that we're going to be adding to this model. And so we'll proceed as regular. So this is just vanilla neural network. We pass through the activation layer, we, multiply by another weight, add to the bias, we have the prediction data for, t+1, right? So for day 1, for day 1, we kind of have this, predicted data. So in this case, working through, in this case, working through like the entirety of the architecture, we can see that now we not only have a new predicted data for day 1. So this is what the model outputs. It's prediction for what day 1's temperature, day 1 stock price is going to be. But crucially, we now have updated the hidden state. So before we didn't have anything, but now during the next cycle, we're definitely going to be making use of this hidden state now. And let's just say that our prediction was right. Let's say that it really was 0.5 was the next day's stock price. My wallet's crying right now. And so what's going to happen is our prediction is correct. The next day, we're going to send as input day 1's data. And the whole goal of this is to predict days 2 data. And this time, we have the help of our little friend hidden state, which captured the relationship of sort of what it understood from day one or from day zero. Yeah.
If we're feeding it to like the part before we do the activation function, why are we taking the data from after the activation function to feed into?
Because it's not from this time steps activation function.
Yeah.
That data is coming from the activation function and the layer before it.
Yeah, but why are we taking like the data before the activation function from the day before to feed into the?
The whole assumption is that the activation function is basically what adds that nonlinearity, right?
Sure.
But without the activation function, our neural network has no meaning because it's just some huge linear combination, okay? So that activation function is really what allows us to add in the additional capacity to understand the relationships that we want to in the data. Because of that activation specifically is what we're saying contains the intuition about what the model understands.
I'm saying since we're feeding it through, like since we're using that like -0.25, like we're gonna add that and then run it through the activation function anyways for day 2. Like
Yes.
why do we need to? I mean,
So let me understand. You're basically saying why are we gonna run it back through another activation function after we've already
just take the first one and like before the activation. I mean, I guess you're saying it's kind of meaningless before the activation function.
Yeah, the assumption there is that the activation itself encapsulates the intuition and the knowledge the model has learned from the relationships in the data, right? So intuitively, look, without looking at like any of like this technical stuff, we want to be able to say, okay, what do you understand by looking at data for time step 1? Take the understanding and then use that to calculate how time step 2 is going to work. Okay, like, okay, what do you understand from how the stock prices shifted yesterday? And use what you've understood about that to predict how stock price is going to work today. And so I want to be able to, the key thing there is I want to be able to isolate how, like, what I understood about the stock prices yesterday. And my understanding, like the part that I understood about the stock prices, is encapsulated by the post-activation and not the pre-activation. Because the activation layer is what imbues it with that non-linearity that causes for us to replicate and modify and replicate and track that those I guess higher level patterns. Okay, so we take the understanding, we grab it after the activation function, and then we're gonna save that. And then the next time step, we're gonna say, okay, this is what you understood from the time step before. Use this to calculate the next time step. Does it make a little bit more sense to everyone? Okay, any more other questions? I'm more than happy to take them right now. Okay, cool. So the next time step through, crucially, we're just gonna be adding, after we add 1 to the bias B1, we're gonna add -0.25 to it. And then we're gonna get our pre-activation value. And then this value is what's gonna pass through an activation in the second time step. And then we're basically gonna get a new predicted data for day 2. All right. Now notice that, this whole time, we didn't really change any of the weights or any of the biases. This is just what a forward propagation would look like. Just feeding in values, passing through the different layers, multiplying by weight by bias, and then previously using the time step before, saving that value, and then using it for the next time step to calculate it. So far, does anyone have like any other questions? Okay, cool. So if understanding it like recurrently with like that arrow coming back to you is a little bit like of a difficulty to understand, I can totally get that. We can go ahead and just unravel this RNN and look at what's happening with like the weights and the biases by themselves, right? So day 0, we basically plug in some input. We have some predicted data for day 1. We update the hidden state. This hidden state will go into the next day's calculations, right where I said it would. And you're going to take in the next day's input as well. So 2 inputs, the hidden state from the time step before and the next input for day 1, calculate day 2. And then the same thing for day 2 and the same thing for day 3. So basically how this is going to work is this is basically how forward propagation is going to work with our RNN. Each horizontal layer is going to be a different time step, and each will have the same parameters. So W1, W2, W3, B1, B2, B3, or B1, B2. We're not going to be changing these throughout the entirety of forward propagation. So one forward propagation is going to look like if I have like a stock prices for like 10 days, like feeding them through from day 0 to day 10, basically. So we're gonna have 10 different layers, and we're basically gonna have the recurrent summation happen like 9 different times. Does it make sense how forward propagation would look on an RNN? So basically, the idea is, if you notice how this RNN is working, you give it some input, you output some hidden state, you move on to the next layer. Now, crucially, if I care about predicting the next value in the sequence, then all these intermediate predictions that we have from day 1 to day 3, they're not as important to us. Because we only care about prediction for day 4. We only care about how stocks are going to look like tomorrow. We only care about how, I guess where the ball is tomorrow. We're not going to care about, the relationship like where it was like 2 days ago, for example. So the whole point of the RNN, in most cases, is the predicted day 4 is the output that we're looking at. And this is the output that we care about. So all of these prediction days from day 1 to like n-1, we don't really care about those predictions for the first couple of days. And so what that means is this RNN is kind of interesting because you give it some input, it outputs some hidden state because that's the only thing we care about at this point. It goes to the next layer, you give it an input, it outputs a hidden state. And it's kind of as if you put some value in, you get another value out, it moves to the next layer, you put that value in, you get another value out, you move on to the next layer. And if you think about it, we've seen this before. This is kind of how a regular neural network works, right, guys? Like if we just, imagine that we have an extra input, and you imagine the hidden state is kind of moving through every layer at the time. The hidden state is kind of representing like its current understanding of all the time steps before, and it's kind of like the memory, if you will, of what the model's understanding of the data. It's just, updating through every single time. Like one node after node after node. This is a really abstract way of looking at it. That's all this is. And every single time step, we're adding, a new value in. We're adding the next input day. And crucially, we only care about the last layer when we output the value that we care about, the day 4 prediction. So I guess, does everyone kind of understand how we can liken this new RNN architecture to just like a neural network? We just redefine the way we define what a node is, kind of. Okay, cool. So what does that mean? That means that the longer the sequence length is, the longer our input length is. If we, scale up from just 5 days to like 100 days, then the deeper this theoretical model is going to be, the more hidden states you're going to have to consider, and the more layers you can imagine of all those recurrent time steps that are happening. So if we kind of like go on this tangent and continue, right? What do you guys think is going to be a big problem that we might run into with really large input lengths? What do we know, I guess, from previous lectures about, really deep neural networks, really deep neural networks and having, problems with those? Yeah.
It can overfit.
Exactly, overfitting. If you have like, 1,000 different days you want to predict for stock price for the next day, then this neural network is going to be ginormous, guys. And every single time that we create a really large deep neural network, you're going to basically be trying to recover a pattern that's really complicated. So it's going to end up memorizing the patterns that's super specific. So that is one issue. But actually, there's a much bigger issue with this. And to get into that, we're going to first just review what happens during forward pass. So, you basically inputted some value in. Yeah, sorry, question?
Yeah, quick question. So, on the last slide, you were talking about a larger network, if you're prone to overfitting. Would a shorter network be prone to underfitting?
That's an interesting question. I feel like at that point, it depends on what we're trying to fit, right? Like if we had something that was like a very complicated relationship, for example, then obviously like having a shorter sequence length won't be enough for predicting it. This makes intuitive sense. You want to predict stocks, okay? Stocks, there's no way you can predict them with just 5 days. The sequence length is not long enough. You're just not going to do good on it. You need to have like a really long sequence length to be able to predict that really well. So in that sense, yeah, you won't do well without having a longer sequence length, depending on the complexity of the relationship that we have.
But if it was like maybe something not as complicated as stocks or something quite simple, you'd probably be okay.
Yeah, and that actually that goes off on a tangent of like, how do we choose like the correct sequence length for our RNN? right? So that is like, that depends on like, what, especially like this problem statement that we're looking at and the complexity of the issue that we're looking at in that moment, and obviously like, data constraints and stuff like that. But yeah, you can say that the converse will always like, be a case. Okay, so forward pass, this makes sense to everyone, hopefully, right? You input a data in, you recalculate using the previous hidden state, and we basically step through and basically for every single input, we have a new Y prediction or a new output, and crucially, the hidden state kind of persists and keeps moving from layer to layer, okay? And let's just say, we have this MSC or we have some loss criterion for finding out how off our prediction or our output is. Okay, cool. Now let's talk about how, I guess, in a basic case, like without RNNs, how backprop is usually working. So I'm sure everyone here, we all talk about backprop in like earlier lectures, right? But just really quickly go over it. We can kind of model the way of changing a weight affects changing the loss. And by taking the gradient and the negative of the gradient, we're able to find out how much to tweak each parameter to better cause a dip in the loss function, right, guys? We talked about this in earlier lectures. But the main thing here is notice how we have to use the chain rule to do this calculation. Because in order to find out how changing W2 affects the loss to move it in the right way, we have to basically look at a composition of functions. Because the output Y prediction depends on A1 times W2 plus B2, right? But the loss depends on Y prediction. So basically, you have this f of g of x scenario here, where the loss is a function of the output and the output is a function of the weight. So chain rule tells us that there's a really neat way to isolate the derivative that we care about, the gradient that we care about, which is the derivative of the loss with respect to W2, and it's by multiplying out the intermediate function that we have. The derivative of loss with respect to Y prediction and the derivative of Y prediction with respect to the loss, or sorry, with respect to W2 parameter. Does this idea of using chain rule to find out the gradient that we're looking for make sense to everyone here? If not, I'm more than happy to go a little bit deeper into it. Okay, and I'll be afterwards. We can always go back into it as well. And this is just like an example of how that would go, right? Take the derivative. In this case, trivially, Y prediction is just going to be A1, right? Because, well, A times X plus B is just going to be A when you take the derivative of it. And then we know from calculus that for L is just going to be the difference between the two. So we can take the derivative of them, find out it's negative 2.4, but then we're going to multiply by that learning rate, or the learning rate, which basically tells us to move in the correct step, but not all at once at the same time. Does everyone understand how learning rates basically work? Yeah, okay, cool. And crucially, we know that if we, try to take the derivative with respect to a weight that's earlier, as in like a layer, behind, or like, back, further back in the propagation, then this is going to be a longer function composition because it's had to go through, multiple different compositions to get there. For example, how does changing weight 1 affect the loss? Well, changing weight 1 is going to affect the variable Z1, which is going to affect the A1, right? Which is going to affect the Y prediction, which is then going to affect the loss. So in this case, we actually have a composition of 4 functions. So this is going to scale up to multiplying by 4 terms for the chain rule here. Does this make sense? Okay, I'm happy to go into this a little bit more in depth, but the main takeaway here is the further back you're going to go to isolate the gradient with respect to a weight, you're basically going to have like that many more compositions because every layer you're basically like adding a new function that outputs like a new ReLU or like outputs like a new calculation for what what the activation is going to be. So essentially, let's consider this, right? And we're just gonna, in this case, we can take the derivative of each one, and we know that for Y prediction is just gonna be W2, or and for 2 is just gonna be 1, and then for 3 is just gonna be X. I'm not gonna go through this because it's just like review from calculus, but I'm more than happy to go through this like later. And just by numbers, this is what it would look like. Multiply by the learning rate again. So imagine I'm gonna go in. I'm just gonna quickly change the weights a little bit. I'm just gonna instantly change the weights here, right, guys? I'm gonna make the weight 1 and bias 1 both negative. And so basically by doing this, let's see what happens now. You give any output you want to get, any positive output, and then look at that. Now the input to ReLU is going to be negative necessarily because you multiply by something negative and you minus something from it. And what is ReLU? ReLU is a function that's just going to either send back 0 or that value itself. And so in this case, since we have something that's negative, ReLU is just going to output 0 again. So can anyone tell me what the problem with this might be? The key thing here is by innocently changing the weights somehow to get to negative weights, no matter what my input's going to be, because, well, in most cases, my input's not going to be negative because I'm dealing with like, stock prices. I hope it's not negative. I'm dealing with like, certain other functions, my input might not be negative. No matter what my input's going to be, it's always going to be a negative input to ReLU, no matter what. So activation will always be 0 for all inputs possible. Anyone find out what the problem of this might be? This might be a little bit tricky, but anyone? Yeah, back.
When you pass it back through, it's always gonna be 0, right?
The back propagation, right? Hit on the nail. So basically the idea here is now, since the input of ReLU is negative, let's consider what the derivative of ReLU looks like. The derivative of a stepwise function is just going to be the stepwise function itself. It'll be 0 and then it'll be 1 because it's just a constant, y equals x afterwards. Anything that's happening before, when we calculate the derivative and we calculate the gradient and we do the extended chain rule approach to do this, the term that corresponds to our activation will always be 0 because the derivative is always going to be 0 for all the negative values. And this made sense because before, when we talked about how the composition worked with like those 4 functions that we had, then we wanted to predict what y prediction was. It depended on the activation value A1. And when we did the derivative of that, we said the derivative of this, the derivative of that third equation was just A1. And because of that, if A1 is always going to be 0, then not only will that one value be 0 all the time, but the entire gradient for W1 will always be 0 because you're multiplying all these weights out. If even one of these things is 0, then the whole thing is going to be 0 necessarily. So that means that if I want to, if DL over DW was like a little bit negative, I might push it down a little bit. If DL over DW2 was a little bit positive, I might push it up a little bit based on the learning rate. But I'm not going to change these weights at all because it's always going to be 0. So the weights will not be updated if any gradient is 0. And this is a problem when all inputs lead to this activation of 0, right? If we somehow during backprop get to a stage where we innocently change the weights to be negative, then we're basically just never going to update the weights, which means we're never going to learn. So yeah. So I guess, this is the vanishing gradient problem, okay? And this is a problem in most neural networks, but this is specifically a problem for recurrent neural networks. We're going to talk about why in a little bit. But the key idea here, guys, is the gradient, during a vanishing gradient problem, the gradient is going to become extremely small or 0 for all inputs, okay? And this is going to cause the weights to never update, which means we're basically not going to be able to learn. Does the vanishing gradient problem make sense to you guys? This is a really big problem in machine learning, by the way. Okay. And okay, so I guess, and maybe I was being a little bit too over exaggerating before. Obviously, if some of our inputs are 0, that's still okay. We'll still have something to backprop on. But if in the case that I had before, it's like all of our inputs were 0. So then no learning could really happen because all our inputs are going to be 0 no matter what. So I guess the main thing for ReLU and for vanishing gradients is that we don't want all inputs to become below 0. And this stays true no matter what activation function we look at. For sigmoid, we don't want them below -5 or greater than 5 for the same reason, because that's like the 0 zone, right? And then for, tan H, we don't want it greater than 3.5 or below 3.5, because once again, it's in the 0 zone. And that's going to cause the same issue that we had with ReLU again. So for all activation functions, it's going to be definitely hard, but it's much harder for those tan H and sigmoid functions because having those two-sided bounds is much harder to keep track of rather than just making sure it's not going to be negative for the ReLU. But overall, this is the vanishing gradient problem. And, like someone said in the past there's always going to be the converse, exploding gradients is another problem. What happens when one gradient is going to be really big? When one gradient is really big, we're going to update the weights up by a lot, which causes another large gradient to be computed, which basically makes this positive feedback loop all the time, right, guys? Like if one of our gradients was really large, then we're gonna jack up the parameter value. And then that's gonna cause, again during backprop, a larger gradient value. And this is gonna cause a positive feedback loop where we're gonna keep on increasing the value of a parameter indefinitely. And this is just gonna be, we can't even learn on this. So does everyone understand the problem of vanishing gradients and exploding gradients, or can I explain it a little bit further? Is there something that I kind of missed? Let me know. Are we getting thumbs up so far? We're good? Okay. Okay, good. Okay, so back to RNNs, right? So we just talked about exploding gradients and vanishing gradients. My claim is that RNNs are particularly susceptible to exploding gradients and vanishing gradients, okay? So let's show how this is gonna be the case. So, okay, how do we first define loss on an RNN? Because we don't just have one output, we have n different prediction days. We only care about that last prediction day for our output, but we definitely want to care about all the intermediate prediction days for our total loss. Why? Because it's a cascading loss, right? Like think about it like intuitively. If we have any loss for prediction of day 1, that's going to compound in the hidden state and cause us to have a terrible prediction for day 2, which is going to cascade again to predict day 3 really wrongly, right? So intuitively speaking, we want to be able to loop in the losses together somehow, because we want it to be able to have a metric for loss that depends on all the intermediate losses. Because then we know if any of the given losses are off, then we're able to backprop on them. So in other words, what we basically want to do is we're going to take the sum of all the loss values that we have from all the different time steps that we have. Okay, so if we have day 100, we're going to have 100 different losses that we're going to sum up, and this cumulative loss is what we're going to say is the loss of our RNN. Okay, and this way our loss doesn't just depend on just the last prediction day. The loss depends linearly on all the prediction days. Okay, and this is basically what we want. So assume there are losses like this, right? Now, how do we backprop on this loss? Well, before we talked about backpropagation, it just happened from right to left because we only had to take care of all the weights and all the layers in only one time step because our regular neural network didn't have more than one time. But really weirdly here, we're gonna have to backprop through a second dimension known as time, right? We're not just gonna be backpropping from right to left, but also visually, if you will, we're gonna be backpropping from down to up, okay? So if you think about how we unraveled our RNN, this really helps us out with backprop now because we kind of want to follow the snake upwards and be able to find out how loss will be computed here. And the idea is the derivative of loss with respect to a gradient, because we summed up all the losses, we're going to sum up all the different derivatives with respect to each of the different gradients that we have. Okay, so if I just want to find the derivative of the loss with respect to W2, well, then we're going to add each of the different derivatives for all the W2s in each of the different time steps that we currently have. Okay, does it make sense? Like, basically, we're going to find out how changing W2 in each of the different time steps impacts our cumulative loss. Does it make sense? So because we summed up all the losses, we're going to be summing up the gradients for every single parameter as well. And then basically what's going to happen is we basically have to deal with chain rule in this case. And as you guys can imagine, chain rule depends on composition of functions. And if we're backpropping through every single hidden state that we're going to have, then we're going to have probably 100 different composition of functions that we're going to have, right? This is going to be a really messy chain rule that we're going to have to do to end up calculating something. And to talk about what this looks like, basically, we're going to have to take the product of all the different hidden states that we're going to have to multiply out these intermediate functions to narrow in on a parameter that was further up rather than a parameter that was further down. And we'll talk more about this in the next slide. If this makes no sense, that's perfectly fine. Basically, the hidden state in 1 impacts the hidden state in all the subsequent layers. We can agree on that so far. The hidden state in layer 0 will impact all the hidden states after it. So obviously then, if you agree on that, you have to also agree that when we're calculating the loss, and we're calculating the loss with respect to a certain weight all the way back there, we're gonna have to consider how this relationship plays out with the different hidden states that are being plugged in every single time. Before, we kind of talked about how we can kind of multiply throughout the chain rules. Well, in this case, if we want to find out the derivative of loss with respect to some weight, we have to start off from that loss with respect to, the 100th hidden state, right? And then multiply out every intermediate hidden state until we finally have the one that we're looking for, okay? If this looks a little bit weird, remember that back then when we talked about initial, or what am I doing? Okay, sorry. Back then when we talked about initial backprop, we did something really similar, okay? We have something that's like this. We're trying to find out, isolate how loss affects W weight 1. We have to start from the outside and work our way inwards. From loss with respect to Y prediction, then Y prediction and then A1, then A1 and then Z1, and then Z1 and then W1, okay? So we're gonna do the same thing here, but unraveling it off, like as we're doing it with different time steps, is basically gonna cause us to have 100 of these in infinity. Before, we had maybe only 4, right? Because we only had one time step. But now, for each hidden state, we're kind of condensing them all into one. We're gonna have 100 of those intermediately. And does it make sense so far? How backpropping through time is going to increase the size of our chain rule calculation by like size, by t basically, right? We're gonna be multiplying it by some factor of t, where it'll be exponentially increasing with respect to like linearly increasing the sequence length. Like if you increase sequence length linearly, you're gonna have an exponential increase in like the chain rule expansion. This makes sense, right? Okay, so and each of those chain rule expansions that we have, we're gonna be multiplying by a W, some weight value. Because before we said that each sort of expansion of each hidden state consists of a multiplication by W2. Because we're always going to be multiplying W2 by that hidden state before we send it to the next time step. We're doing this every single time step. So then we take the gradients, we're also going to be multiplying by W2 at every single time step. So approximately, we're going to have some W, some weight value, some weight, and not just for W2, but for each of the different weights. But without loss of general, let's just focus on one weight for now. This weight will be repeated and multiplied by itself 98 times. So what I'm trying to say is that when we do the chain rule expansion, there's going to exist some weight in our chain rule expansion that necessarily has to be multiplied by itself 98 times by necessity, because each of the composition of functions that we had one multiplication by that weight. And we're composing them all together, taking the derivative of all of them. So we're going to have 98 times or some t times or t minus n times of that weight multiplied by itself. Does this make sense? Now, this is the problem, because even if that weight was something super small, like 1.2, then that gradient is going to become massive. Just by, how algebra works, that gradient is going to become super massive. And conversely, if that gradient was any value from 0 to 1, then after taking like 98 to the power of 98, if we just had even 100 in a sequence, which is not even enough to predict anything, we're going to have some extremely small gradient. So basically, the claim that I'm making to you guys is as our sequence length increases, at some point, our sequence length is going to become so big that no matter what, our gradient will either always explode or always vanish. Because our chain rule expansion is so long. Have I convinced you guys of this? Does this make sense? No matter what, as that chain rule becomes super long, this is always going to result in an exploding gradient or vanishing gradient. And obviously, it's not going to be like a big issue in all the cases because remember, we're going to be adding each of them together. So if we have like vanishing gradient for like, say, say like we have vanishing gradient for like, the first 2 layers, then when we take the sum of all the gradients, then we're going to realize that the gradient's never going to rely on the first couple of gradients because these gradients will always be 0 no matter what. Like, remember when I said that we're going to calculate the gradient based off the summation of all the different initial time step gradients? If for t equals 1 and t equals 2, the first couple of time steps, those will be the ones that have a really long chain rule, right? So for those ones, you're gonna have, either vanishing gradient or exploding gradient. If you have vanishing gradient, then they're not gonna be responsible towards the overall summation calculation because they'll just be 0. So what this basically means is, funnily enough, we have discovered that this RNN is gonna forget what it's gonna learn from the earlier time steps. It's forgetting, right? Because from the earlier time steps, if that gradient were to vanish, then it's not gonna be able to use those earlier time steps to calculate the overall gradient.
Well, if W is like greater than 1, wouldn't it like over remember?
And then it won't even work, right? So maybe let me be more precise. Either we're gonna have a vanishing gradient case where we can't, really benefit, or we can't really learn from the initial weights, or we're gonna have an exploding gradient case where the summation is gonna be super large and then we can't learn anyways. So overall, the claim here is in either cases that you choose, exploding or vanishing gradients, we can't learn long-term memory. We can only learn it when our sequence is really short. Because then we're not gonna have the problem that I said, we're not gonna have really long chain rule. So the fundamental weakness of an RNN, we proved it so far, right? The fundamental weakness of the RNN is it has short-term memory loss, or maybe I should say long-term memory loss. It's not able to remember things that it's learned in longer memory. And by memory, I mean those earlier time steps. And I'm basically saying if you had a really long sequence length that we're trying to predict like stocks are for like, let's say 1,000,000 days, there's no way that those earlier days are going to be anywhere responsible, and it can't even function like that. So basically the idea here is that this idea of an RNN is not good for long-term memory. It's not good for long-term it's not good for older time steps. And for the short term, for newer time steps, it's going to be prone to big changes by design, because it's not going to be able to have as much data to train on. So we don't need to calculate the older gradients for that. So far, just up till here, yeah.
Wait, doesn't that kind of fix the problem?
What do you mean?
Like not considering the very old, like the very old data. Because you were saying like.
Right. So initially I said that like when you have a really long sequence length, right, then you're gonna have a really deeper model, right? And that deeper model is gonna contribute towards overfitting because you're gonna have a really deep architecture, right? So I guess what I'm trying to say is that those are both issues that we're gonna have, right? So it's not that one of them is gonna counteract, like it's not that they're gonna work against each other to counteract one another, is that they're both gonna be present inside the model. Because on one end, you have this really large model where they're gonna be trying to calculate gradients, and then have that, it's gonna be multiplying over time. And because of that, like either it's gonna be vanishing gradients and the earlier ones aren't gonna work towards it, we're gonna have exploding gradients, it's not gonna help us out at all, right? That's one weakness that we have, right? But then on the other end, the longer the sequence length gets, right, then the more prone that we are towards overfitting. Okay, so it's not like overfitting and this idea of like vanishing gradients that we're forgetting the gradients earlier are kind of related, as like they're not going to counter each other out. It's not like all of a sudden we're gonna have like a smaller input length. Okay, we still have as many layers as we had before in our model.
It's just gonna be wrong. It's finished or exploded.
Yeah, basically the idea is no matter what, we're gonna have vanishing and exploding gradients. That's one issue. The other issue is that as the sequence length increases, the RNN can't handle, like it's gonna be prone towards overfitting, right? So I'm trying to make this claim to you guys. I'm trying to convince you guys that like no matter what, this idea of longer sequences and RNNs are just not going well together. Okay. So basically the solution to this is this idea of LSTMs. Okay. And because of time, I'm just gonna quickly kind of brush over this. And as long as we talk about the main idea, it's not gonna be that bad. But well, I guess we'll answer questions after I talk about LSTMs then. Okay. But the main thing is we want to be able to have access to long-term memory. Okay. We want to be able to have access to what the model understands from the earlier time steps. But the longer our sequence length is, the worse it's going to be for us to not fall prone to the issues that I said before. Okay. So how about we do this? Okay. how about we take this concept of long-term memory and we separate it away from this concept of short-term memory, okay? And then what we want to be able to do is say, okay, here's my long-term memory. I'm only going to update this when it actually matters, you know? And I'm only going to increase that long-term memory context length when I actually care. But in the short-term context, I can be as dynamic as I wish. And the intuition here is simple. The problem that we were having before is our long-term memory is becoming too big. Well, we didn't really have a definition of short-term versus long-term memory, okay? We didn't make that distinction. So our capacity is becoming too big for the model to understand. In other words, our long-term memory was becoming, our memory is becoming too long-term. So let's stop that from happening. Let's keep the long-term memory separate from short-term memory and have those two play a disjoint role. And if this makes no sense, we'll walk through a concrete example and hopefully this intuition will play a little bit more in the future. But at a whole, this is what an LSTM looks like, okay? And it's not really like based off of like, you know, a regular neural network structure that we always have. It's a little bit of a different architecture. But basically, an LSTM block is defined as just this one chunk right here, okay? And to be honest, there are 4 or 5 parts to this LSTM, okay? And we're going to talk about each of these parts in more detail. But for now, the idea is from one time step to another time step, this block becomes recurrent. So the output of this is going to feed back inside somehow, okay? And we're going to talk about how this is going to work. So for now, just understand LSTMs, it stands for long short-term memory, okay? So a specific type of architecture that is an improvement upon the RNN, okay? And it is recurrent still in nature because once we define what a block is, that block will recur over time, depending on how the inputs will go back in. Okay, so let's talk about how a single block is going to be. And before I'm going to show you guys the entire image, I want to tell you guys that the different parts of the image is something that's completely like not new at all, right? You guys know every single part of this individual image individually, but the new thing is how we're presenting them together. So each of these terms you're going to see down here, they're just the weights. Remember, we're just multiplying weights by some value, right? The same weights we've seen in the previous lectures, okay? Each of these values over here are the biases, okay? We're just gonna be adding these values, you know, throughout layer by layer or block by block, okay? These have not same biases, okay? And long-term memory is the new thing, okay? So we're basically gonna have 2 types of hidden states. Before we had only one hidden state that would persist from iteration to iteration, right? We're gonna separate that hidden state into 2 hidden states now, okay? We're gonna have one that's only updated like maybe not that frequently at the top. This is our long-term hidden state, if you will. This is our long-term memory. We call this the cell state, CT, okay? At the bottom here, we have another passage information flowing through, okay? This is gonna be our short-term memory, all right? So green line's long-term memory, purple line's short-term memory, all right? Okay, so now I've warmed you guys up to this entire picture at once, all right? So what's going on over here? So basically, this LSTM model is a gate-wise structure, which means it depends on different gates that process the flow of information or activations, if you will, right? When I say the word informations, I want you guys to think about that hidden state, okay? The hidden state represented the understanding of the model at a certain time step up to that time step, right? Like, how is the weather up to this time? How is the weather up to that time, right? Understanding intuition up to a certain time, okay? So when I'm talking about like gates, I'm talking about like how that hidden state or that latent representation is moving throughout the model, okay? Can that abstract idea make sense to you guys? Do you guys get what I'm trying to say with that? So basically, there's 3 gates that you have to know. First is the forget gate, okay? The second is the input gate, and finally we have the output gate, okay? So let's talk about this a little bit more in detail. So let's just focus on the forget gate. It's composed of an input. This input is just what we've seen before, right? just at a given time step, what is the weather at that time? Or what is the weather on that day? What is the stock on that day? This is the same input that we've seen in the RNN, right? We're just gonna chuck it in at the bottom here. This input is gonna be multiplied by a weight, added to a bias. But crucially here, we're making one notable difference. Before we add it to the bias, you guys remember in the RNN, when we added to the hidden state of the state before? Here, we're gonna add this to the short-term memory, which is the short-term memory state, the hidden state 2, the second short-term hidden state that we had. We're adding that to this input, basically. Okay? And we'll talk about this later. But basically, what this is going to show us, or this is intuitively what this means, is how much of the previous short-term memory at t-1 are we going to be paying attention to? And how much of the input are we paying attention to? So the idea here is that weight is multiplied by the input. So the weight is corresponding to the input. How much of the input do we actually care about? How much of the input are we paying attention to? Okay. Now, that second weight that we're multiplying, that 2.70, that we're multiplying times the hidden state, or times the short-term memory state, is how much of the sorry, how much of that short-term memory are we paying attention to? So basically, you can think about it like, oh, if if this was like 100, for example, if this was 100, for example, then, oh, we really want to pay attention to short-term memory right here on this time step. It matters a lot in this time step. In this time step, it may be the case that currently short-term states matter more for the loss, which means that currently this area of time matters more for my prediction, and not really the overall progress of how it's working. Perhaps just that month of monsoon season is important for predicting the flood, and not the entire year. Okay. And conversely, if it was a really low number for that 2.70, it was 0.05, then it's okay, we're trying to predict something that's more persists throughout the year, for example. And then we don't want to pay that much attention to the short-term hidden state or the short-term understanding at any given time step. Makes sense overall, guys? Okay. And then we're gonna pass this through a sigmoid function. Okay, so we're gonna sum these, and then we're gonna add the bias, and then we're gonna pass this through a sigmoid function. Okay, and if you guys know what a sigmoid does, is it maps an input to some value between 0 and 1. All right, so why do we want this? And the thing is, think about percentage. Okay, we want to be able to map this to some value that can tell us how much to pay attention to the long-term memory, or how much we want to keep in the long-term memory. So let's say, we have our input, we multiply by 1.63, okay? We have our short-term memory, we multiply by 2.70, okay? Now we add these together and then add a bias on top of it, right? So now we have this amalgamation that kind of shows us this is our input that's coming in, and this is how much we're gonna pull from the short-term memory. Okay. Now we're going to connect this to our long-term memory. And what we're going to do here is by passing through sigmoid, let's say that our sigmoid outputs something by 0.5, for example. Okay. It maps to some number between 0 and 1. Or in this case, it's 0.99 with the numbers that we currently have, right? We're going to multiply this number by our cell state, by our long-term memory state. And this is going to tell us how much to remember of that long-term state. It's kind of called a forget gate, but in reality, it's more like how much to remember in the long-term memory state, if you will. But the main idea is we're doing 1 times the CT, we're remembering everything in the long term, okay? And we're doing 0 times the CT, we're forgetting everything in the long term, hidden state. And basically, you can think about how this is a control structure on the hidden state that we have for a long term, right? At any given time, we choose how much of the long-term representation we're going to use towards prediction and how much of the short term we're going to use towards our prediction. Anyone have a question on the forget gate? And then basically now, this CT that passes to the next gate, which is the input gate, is not the same CT from the previous gate. It's this updated CT that's been multiplied by that one weight that we had before, right? By the activation of a sigma wave function. So in this case, we actually have two things that are happening here, right? In this input gate, if you recognize the left hand here, it's basically just another, example we have from a forget gate. We're gonna choose, how much of the long-term memory to remember. On the left-hand side, just another forget gate. Short-term memory unchanged. And on the right-hand side, we're gonna generate a new long-term memory from short-term memory and the input that we have. So essentially what's happening here is on the left-hand side, we have like that bias that basically goes through, like everything that happens before happens again. And we're gonna basically choose how much to remember of the long-term memory. On the right-hand side, all we're doing is we're gonna find a way to generate a new long-term, update the long-term memory input from short-term memory and the input that we currently have. Okay? So I guess the new thing here is only the right-hand side, because the left-hand side is what we talked about before. But on the right-hand side, we basically have two weights that multiply by the input. That doesn't change again. This is the same input as the,
So what is the reason for like choosing how much of it to remember and then immediately choosing how much of it to remember again? Like, why do you do that twice in a row?
And the difference here is how it's being used to update CT. Okay, so notice how both these blocks are being used to update CT together, right? Before it was used as in like the previous time step, as long-term memory was coming in, it was a preliminary step to update that, right? But now in this block that we currently have, it's kind of trying to find a way to add on to long-term input, and it's to pull from short-term input again to do that. So in this case, the forget gate is gonna make an other appearance here to add again to long-term input, right? Because the first one was just to kind of tweak the long-term input that we currently had coming in to go into it. Does it make a little bit more sense?
Yeah.
Okay. So basically, how much of the short-term input to pay attention to is what's happening here. Because our short-term state is coming in, multiplying again by a weight, and this happened in the forget gate before. We're just gonna choose some of that, right? And then our input, which is the same input as everything in this time step, so this is all one time step, right? Is gonna be multiplied by another way to choose how much of that input to pay attention to. And then we're gonna feed this through a tan H, okay? So not a sigmoid, because in this case, we're not trying to convert this to a value to multiply to as a percentage to like take some of it, right? To extract some percentage of that value or to understand some percentage of it. In this case, we're gonna perform a write operation. We want to be able to add into that value here, right? So the tan H is basically going to output between -1 and 1, just to put a bound on the update to make sure we don't have a really large update. Again, to curbside this idea of preventing against exploding gradients, okay? And then once I make it to the last game, we're basically gonna wrap up. So hold on for just a couple of minutes, guys. That's my bad. Okay, so this is gonna provide a new CT value, right? And crucially on the left-hand side, we're gonna choose how much of that value to keep, right? Choosing how much of that new memory to forget. And to go back to what Seth's question was from earlier, we are multiplying these two values by each other. Okay, the forget gate shows us how much of long-term memory to remember. On the right-hand side, we have a new offering for what the long-term memory should be. Multiplying them now gives us a new value for what the long-term memory, how much we're going to take. Okay, and we're going to add that back up and update that into our running total for our long-term memory. Make sense, guys? Okay. Finally, we have the third gate, which is the output gate. Crucially here, the short-term memory output right here is what's going to be the output that we care about. This is the prediction for the next time step. This is the one that's going to loop back around and be used to predict the next time step t+2. And so this is what we're going to call the output gate. Once again, if you guys remember, the left-hand side is just another forget gate, right? It's the same as what it was before. This didn't change. And this whole time, short-term memory is unchanged. even the previous block, it was unchanged. The long-term memory is changing from every single gate to each gate. In this case, we're kind of like, restriction information flow in the case that we want it to be. And on the right-hand side, we're gonna pass in the CT that's been, forgotten and added to through a tan-H, right? And what this is basically doing is that CT that we initially had, this updated CT, is gonna pass through the tan-H value. It's going to, come out to some value, shrink it down like huge, like, long-term representation down to like, some value from -1 to 1. And we're using tan-H here to shrink values and not sigmoid because this is gonna be our new short-term memory. So multiplying the output of the sigmoid and tan-H to get a new short-term memory and how much to keep. And this new short-term memory is also the final output. Okay. So to put it in perspective again, on the left-hand side, we have the forget gate. This passes through a sigmoid. How much do we want to remember? Okay. The long-term basically is shrunk down and it's offered as a new short-term value. We multiply these to remember some of that short-term information that'll persist in the next step. So this is a very beautiful push and pull, plug and play, or I guess it's a very beautiful push and pull relationship between short-term memory and long-term memory, right? Every single step, we kind of choose how much of long-term, short-term to pay attention to. We offer either a new long-term or we offer a new short-term. A new long-term gets offered from a short-term value. A new short-term gets offered from a long-term value. And in this case, we make sure that every single time step, this is going to loop back again for the next time step with a new input. And every single case, we are going to make sure this way we're only periodically updating the long-term when we absolutely need to, when the weights determine that they're important. We periodically or dynamically, change the short-term ones, depending on how it goes through the model again, as the weights need to. And this way, we learn to pull from long-term presentations for overall general picture, big picture stuff, and the short-term for just in that moment, how to use it to calculate the values that we need to. Okay. Any questions on LSTMs, guys? Are you sure? That's a lot. Okay, fine. Yeah, just difference between sigmoid and tan-H. Hopefully you guys understand that. And then final thing, GRUs. I'm not gonna go through this, but basically this is a simpler version of an LSTM. You can see they're defined as an extension to the RNN, the same way LSTMs work. They're still recurrent, but the red ones are just gonna be, sigmoids, blue ones are gonna be tan-H. This is just another one that's useful for you guys to know. It's simple architecture, which is less computation, and less training time. But it might train faster than LSTM because it's much more simple architecture. But LSTM provides more control over the memory that we have because it simply makes a distinction between long-term and short-term memory. The key thing is the GRU only has long-term memory. So yeah. Yeah, and then you can use RNNs or LSTMs to do word prediction, which is a great application of it. So yeah, next time we're gonna talk about transformers. But until then, yeah, thanks for being here. Sorry for running a little bit extra. My bad.
Not next time, but in 2 weeks, we'll talk about transformers.
Yeah, 2 weeks, guys. Sorry about that. And what are we doing next week?
We're doing auto encoders next week.
All right, thanks, guys, once again. First lecture, so sorry if it was a little bit weird. Wait 1 second. I'll be taking questions over here, so just make a line. We'll address any questions you guys have. See you guys next time. Thanks, guys.
Thank you.
Yeah.